Today we're going to look at solving the Schrodinger equation for the one-dimensional particle in a box, and we're also going to derive an expression for the energy eigenvalues for that system. So the first thing I'm going to start with is the Schrodinger equation. I'm going to start with in 3 dimensions, and that is negative h bar squared over 2m. We have the Laplacian, the wave function, plus the potential acting on a wave function, and that's equal to I h bar times the time derivative of the wave function. And I'm using this notation for the Laplacian. Just so we're clear, I'll write that out. So this is in 3 dimensions. This is not time independent, and this is also importantly in a Cartesian system. We're not dealing with any other systems that aren't Cartesian. But we're only concerned about the one-dimensional case. So I'm going to write this in 1 dimensions, and that becomes negative h bar squared over 2m times del squared psi del x squared plus potential function times psi equals negative I h bar del psi del t. This is good. This is a bit simpler, but for this particular system, I want what's called a stationary state solution. So I don't want any sort of time dependence. Time independent Schrodinger equation then is, it looks really similar. It is the left-hand side, the exact same. I'm going to switch to ordinary derivatives here. Second derivative there, potential function times psi, and this is the energy eigenvalue times psi. This is the sort of very nice Hamiltonian of the wave function equal the energy of the wave function is what this one down here is, and this is what we're going to be working with for the one-dimensional particle in a box. And really, at this point, once you get to the some logical steps to get here, your problem is sort of defined by what this potential function looks like. So for particle in a box, I'm going to define a potential. I'm going to call it v of x. And I'm going to give it a piecewise definition. And I'm going to say that it is plus infinity for x not in the well. We'll call that 0 to L. I say that it's 0 for x in the well. Alright. So at this point, we have our potential function. We have the equation we're trying to solve. It's a second order differential equation we want. First, we're going to solve for the wave function first, and then the energy eigenvalues. So what do we do next? Well, we can sort of interpret the absolute square of the wave function as a probability distribution. That is what it is. And from this potential function, we know that there is 0 probability that this particle that's described, that follows this Schrodinger equation here, and this potential will not be found out here where there is an infinitely high potential barrier. So I'll write is probability distribution. So we really only care about what's going on in the bottom of the well where the particle actually lives and is found. So with this sort of interpretation and consideration, we can write then our Schrodinger equation is negative h bar squared over 2m, say del squared psi del x squared. I'm going to write it like this. So this is 0 times psi. This is the energy times psi. Well, this just goes to 0, so we have equivalently negative h bar squared over 2m d squared psi dx squared equals e psi for the inside of the well, because we don't really care about what the particle's not. And it's 0 where it is, the potential is 0 where it is, so we just get this. This is a really well-studied differential equation. You could solve it sort of from the beginning if you wanted, but I like being clever, and realistically making an ansatz here is going to be better and more efficient because it's faster, you save time. And because this is so well studied, we know that the solution is going to have the form, we're just going to say ansatz, so we're going to assume that psi is a function of x, because we want a stationary state solution, some constant a, cosine little a, the argument, plus b sine little bx, and these are sort of two solutions, so a linear combination of those two solutions is also a solution. So we're going to work with this, and this is what's going to ultimately give us the wave function, stationary state wave function for this particle in a box. So now we need to work with finding these constants. So we have a skeleton of what it looks like, and we need to use boundary conditions to figure out what these are going to be. So the first boundary condition, keeping in mind this definition for a potential here, is that we want psi of 0 to be 0. This is the first one. And the second one is that psi of L we want also to be 0. And this is the second one. And then we'll have sort of a third boundary condition that is important but not listed here in a second, but we'll start with the first one. And so we know that if we want the argument of this function to be 0, and we want the whole thing to evaluate to 0, there cannot be a cosine term. So cosine goes away. So from here, we get this psi of x equals b sine little bx. So this is already really nice. We got rid of one of the terms. We're down to one term now. We just need to figure out what these big B and little b are. So now we go to the second boundary condition, and now we say that, oh, okay, well, psi of L is just 0, and we're saying that L is the end of our well. We have 0 is equal to b sine of BL. And the only way for this to be true, we don't want to restrict our solution by saying that b is 0, because then we get a trivial solution, and we don't care about that really. It's not interesting. The only way for this to be 0 is for the argument of the sine function to be such that sine is 0. And that happens when the argument is an integral multiple of pi. And this is actually where, for the way we're doing it, where this integer comes in. So now we have n pi equals BL. It's super straightforward to see that B is then n pi over L. Okay, this is good. This is time to celebrate. We did something right. Now we have then that the wave function, stationary state wave function, is b sine of n pi x over L. Great. This is good. But we're not done yet, because we still have this ambiguous constant here, big B, that we want to figure out. Now, the boundary condition that I didn't mention up here, but we can sort of treat as one, is the normalization condition, where I'll write it for the case in one dimension, where we have the integral, that's a bad integral, the integral of the absolute square of the wave function over all space with respect to its spatial coordinate is equal identically to 1. It's the normalization condition. Normalization condition. And this, what this is really saying is that there is some probability of finding the particle somewhere within our well. And by integrating this absolute square of this, we don't really care about the absolute part because everything is real. So just the square of the wave function here. We integrate it, if it's 1, it gives us a value for b, and then we have our wave function for stationary state particle in a box. Great. So now we're going to do that, but we're going to break the integral up first. So I'm going to use some sort of like maybe abusive notation and say that for us, we have the integral from negative infinity to 0 plus the integral from 0 to L, and then L to plus infinity. Well, remember earlier we said that we interpret the absolute square, or in our case, because we're real, just the square of the wave function as a probability distribution, and there is no way that this particle is going to be able to tunnel through those potential barriers because they are not finite. So this goes to 0. this also goes to 0, and we're just left with this. So we have that 1 is equal to the integral from 0 to L of the wave function squared. We don't really care about the absolute part, everything's fine for now. Sine squared of n pi x over L dx. This is nice. I'm going to move things around, use some nice trig that I know actually that's requisite. And I would just have that this is 1 minus cosine 2 n pi x over L. The 2 is important there because we should all know this at this point, but n squared of alpha is 1 minus cosine 2 alpha over 2. We should know that, so I'm not going to keep it there. It's just something you need to know how to integrate the square of a sine or cosine function, similar. This is really an easy integral to do. We just get that this is b squared over 2, that stays the same. And then we get that this is just x from 0 to L minus L over 2n pi sine of 2n pi x over L, also from 0 to L, by our favorite fundamental theorem of calculus. Also super easy to evaluate. I'm not really going to expand it, but I know the first term here is just going to be L, and the second term here has to be 0 because sine of 0 is 0. This whole thing vanishes. Sine, well, this argument evaluated at L is an integral multiple of pi, which we already know that sine of that argument is 0. That's what we used up here. So that also goes to 0. So we're just left with L. And so this is just L b squared over 2. And we know that that is 1 based on our sort of chain of equalities here. Now we can solve for b. And b is nothing other than 2 over L under the square root, if I can write it nicely. Now we have our complete stationary state wave function that is this constant b, which is root over L times the sine of n pi x over L. And now I'm going to say sort of explicitly that n is a positive integer. So this is where this number comes from. If we were doing something a little bit more sophisticated in quantum mechanics, we would say that that's the so-called linking constant from solving this thing using separation of variables. That always happens. It's actually the basis for quantum numbers in general. But for now, this is exactly what we want for the wave function. We said we're also going to get the energy eigenvalues. And getting that is really simple. We already did most of the work. Now we just have to plug things in and solve and simplify. So our Schrodinger equation in one spatial dimension, time independent, is this. So x squared. We said that this potential term is 0, so I'm not going to write it for the domain where we're inside the well, and this is just energy equal to the energy eigenvalue times the wave function. So this is good. So we're just going to solve for E at this point, just straight up solve for it. And before we can do that, we need to know what the second derivative of the wave function is, which we just found. Not a problem. So I'm going to differentiate it twice, and we get that this is 2 over L, that factor stays out front, and then we get a n pi over L cosine of n pi x over L. These derivatives are all for here pretty straightforward. Second derivative is then 2 over L times, we'll say a negative n pi over L squared, and then the sine pi x over L. Now we have our second derivative. We just plug everything in now. We'll see that a bunch of things cancel. a bunch of factors cancel, we can just have something for e. So now we get negative h bar squared over 2m, and I'm just going to throw everything in these square brackets, and this is n pi over L squared sine n pi x over L equal to e times root 2 over L sine n pi x over L. Okay, sort of ran out of space there, but we'll see that lots of things cancel, so the terms where we have a sine function go away, the terms where we have root 2 over L go away. All very nice. This negative sign goes away. Now we're just left with h bar n pi squared over 2ml equals e. And this is what we want, so I'm going to just write this a little nicely. So I'm going to define energy levels with respect to n as this e, so energy eigenvalues for each n, and this is equal to n pi h bar squared over 2m L squared. This is supposed to be squared, sorry. And now we have this, the energy eigenvalues that we wanted. So this is it. We're done. We got the results we wanted, so I'll just write them down here again. Stationary state wave function. We found that this was just psi of x. We're taking x to be a real valued number, and this is just root 2 over L times the sine of n pi x over L. Very nice. We want the corresponding energy eigenvalues. Writing is not very good on this little tablet I have, and we just say that with subscript n. That's just n pi h bar squared over 2m L squared. That is an h bar. And then we're done, and I'm just gonna finish this by saying n is a positive integer here, and I use this notation for that because it's nice and compact. And that's all. That's all you have to do. So really, we just solved the time-independent Schrodinger equation in one dimension for this really nice potential here for the one-dimensional particle in a box. Applied some boundary conditions after getting the skeleton solution to figure out what terms we have and what the arguments of those terms might be as trig functions, and then we applied the normalization condition to find the amplitude of the leftover term, the sine term. We found it's root 2 over L, and then we have our wave function, and then we just threw everything back into the time-independent Schrodinger equation in one dimension and solved for the energy eigenvalues directly. And that's really all there is to do. Yeah.